J theta double dot is what? Torque. Torque. Current. Dimensions don't match. Alright. I don't know who wrote that. I'll have to dig up the evil person who did that on that last. And I went back to their old house. But I used my numbers before it confused me. And I'll tell you what those are. For the state model, you can try this if you wish. I think everyone got that concept is B over equivalent friction over equivalent inertia. Sage and theta, omega. And the inputs, this is actually quadrant. It's right up all the terms. You can see what they are. And J equivalent for this system is 2.01, it's 10 to the minus third. And that is in kilograms meters squared. B equivalent, 5.1, which is 10 to the minus 4. That's Newton meters per radian per second. All right. This is the gear ratio. Because really that motor's going through the gear to drive this whole system. Eta sub G is the efficiency of the gears. Efficiency of the gears. Eta sub M is 0.69, and that's the efficiency of the motor. And KT, torque constant, 7.69 10 to the minus third, and so that's the torque constant. But use those numbers, we get this number is equal to minus 0.2427. And this whole big number is 158.9. And those work very nicely. Yeah, the one thing that I haven't covered in the will is the input. When you choose the desired poles, and I think the desired poles were what, minus 10, minus 10. And anyone notice if you put that into place, what happens? You solve it directly, it's two equations to a node, really easy to solve by hand. But if you use afterwards replace, what happens? You wouldn't do that?
gives you an error.
Here's an error. All right, it can't handle repeated routes. So what you have to do is make one of these a little bit different. All right, just change it a little bit. Very slightly. And then it's a numerical problem with it. If you make it very close, but not exactly equal, it'll work. All right. And that's a numerical problem with the way that algorithm works. But, you know, 10.1, 10.01, yeah, same thing, pretty much.
Will that have a problem with the others? I'm trying to remember what the other MATLAB functions similar to Accurate.
Well, it's accurate and place.
Oh,
It's called place. Yeah, place will give you that error.
It would.
Yeah. Yeah. Place will give you that same error. But it's really easy to overcome. Just don't make them exactly the same. Make them really close. Yeah.
Well, I just wanted to comment, because I did that last time on homework, because it has like a repeated -5 group, I think.
Yeah.
So like, after work, the place did.
After work on that one?
Yeah, it did.
Oh, okay. Okay. Yeah. But what I do, especially since, you know, this is a physical system, this is a model for a physical system, if they're not exactly the same, who cares? It's an approximation anyway. So, easy way around it. Now, about the inputs. This is really to make a regulator. So here's my plant. We did here for 2 states, beta and omega. Going into my gains. What do we call them? And add them up. And drives the plant. No, I look regulator. Yeah.
Quick question, on this board right here, in your B matrix, is that NGN minus NKT over JT?
No, minus this is NG times NM times eta.
Oh.
Eta G, eta M, eta, they're all multiplied.
Cool.
Efficiencies all multiply together. Okay. So, what are you giving me a step input? So I need something here. Basically, it's just a scaling in this case. All right? Does it matter if I'm trying to verify if my system actually has those closed loop rules? What the input is? No. Why? In principle, I could put anything here. Why could I put anything there? If it's a linear system. So I'm really trying to verify, does my final system hit those 2 poles? Is it critically damped? Why doesn't it matter what the input is? Or the magnitude of the input versus for a linear system? Discuss it if you wish.
You're talking about saturation.
Well, talking about linear system, saturation is not linear. If it's purely a linear system, does the magnitude of the input matter? Or is the closed loop poles? Yeah.
Isn't, it won't change the characteristic equation.
No, it doesn't change the characteristic equation. That's the point. So it doesn't matter what it is, if it's truly a linear system. Right? Because I'm really looking, these are based on characteristic equation. What's the input to a characteristic equation? That characteristic equation is what? Bunch of stuff equaling 0. It's a homogeneous equation. It's got to do with the input. Now, what you have to watch out for, however, is a physical system, as you said, things like saturation. Right? If I saturate, it's no longer a linear system. So you want to make sure your inputs and things are small enough that they don't go out of bounds, don't go out into saturation. Right? Now, but you can play with this. In fact, anything goes here. So how are you going to verify that this actually had the right, physical system had the right? what should the response look like if it's a critically damped system?
No overshoot.
No overshoot, and it should be like this up to whatever the final value is. Right. And what that final value is, since I don't care. Right, for this. So then we've got, how am I going to evaluate this? Well, what's this theory say it should be? In fact, it says compare simulation with actual. What's the simulation? How do I simulate this? What's that?
LSIM.
Easier than LSIM. LSIM works. Step input of what? A closed loop system. How do I make a closed loop state system? We did that. So my original system, right? And what I'm going to do is, we're going to replace this with, because I'm now putting feedback in here. The input is k times x, right? So my closed loop system is what, A plus or minus, it makes no difference, plus B, K, X. And if I want, I can have B times other inputs. I'll do other. Right. What's that? A plus or minus, depending how you define your K's. BK. What is A plus BK or A minus BK?
Closed loop.
Closed loop A matrix. So my closed loop system is simply what? Call this A closed loop. A closed loop. Oops. There it is. My closed loop system. B, C, D matrix don't change. So I put that into the system, just definitely put it on it and see how it compares. So what I would look for is, hey, does it get to the final value in about the right times? Yeah.
Can we also use the MATLAB feedback command in this?
You can, yeah, you can do that. It'll do the same thing. What you have to be careful for there is where the feedback is coming from. So if I do the thing where I have the entire system, I define my ultimate system as a sys. I do system equals state space A, B, C, D. I do that. Then that's not going to work very well. Because what it's assuming is you Y out here. Right? Not states. Right? And so if I do that, input Y, output U, that's not K. What is it? Still do that, but what's that block?
Isn't it just unity?
What's that?
Isn't that just unity feedback right there?
No. Remember what we're doing as observers? We combine the controller and observer together, we call that a block. Right, that's scripting. Okay. It's empty out there. Those are regulated. Inputs the output of the system, output of the regulator, input of the system. So if you do that, then you use feedback. So you can't just use feedback with K because if I define this system, it's Y, and that's not what you have over there. thing, but be careful what you're feeding back, what the loops are. Okay. Just make a little more sense. Questions on this? I apologize for the thinking, oh, last year's lab would be just fine. You know, there's stuff. I should have given you, in fact, what I'll do is put last year's lab, first lab, on the thing you put through it, with all the numbers. And actually, it's very great to observe. And there are two programs that we wrote, and Tia and I wrote this last week, that were really nice. One of them just does state feedback, and works beautifully. The other one does the observable regulator. The problem with that, when I was trying to use the state space block for that, it doesn't work in real time. So you have to go there, and it is this little C code block. You just have to put in the A, B, C, D matrix of the regulator. And it works very nice. And that's written up on this paper. Check that this afternoon. Make sure he has the right one. We forgot to check that he had the only right. Yes. Observer regulator. All right, then, there's an extra part for those in the 6,000 level, where we talked about today, which is the minimum order measure. Did everybody get the homework okay? It wasn't until yesterday that someone asked what's the order of the, what are the actual states of the pendulum problem, what order? So I was amazed, that, okay, Monday to do tomorrow, and someone finally asked that question. Yeah, what else is good? We're going to come back to that problem. In fact, the last lab is you're actually going to implement an inverted pendulum sword. We have one with the launcher system that same base thing, but it has this little inverted pendulum that can balance. You can make a balancing pendulum. Kind of fun when it works, and you have to be careful when it doesn't work.
Are there 2 labs or 4 labs in this class?
3.
3, okay.
There's a controller one, feedback one, observer one, which will close today, tomorrow.
Okay.
And then the last one will be make the inverted pendulum. And they all get lumped into homework, of course.
Okay.
Yeah.
When's lab 2 due?
Well, I haven't posted it yet. I can post it. I give you 2 weeks. It should be relatively straightforward. If you're familiar with the launcher stuff, it's a matter of putting in your regular gains and controller and observer gains, and we did it in like 5 minutes. Yeah, 30 minutes actually wrote the code. Really good. Yeah.
With the minimum observer, minimum
Uh-huh.
order, is the reason you would go with that over just a full observer for computational complexity, or is there something?
Well, let's talk about that. Good lead-in. What we're done so far with these observers is we have done what? We've made an observer for every